Hello, teachers. So today we're going to continue chapter 1 and we're going to discuss explorations with patterns. So chapter 1 has 2 sections only. I know there's a lot in both sections. Section 1.1, which is problem solving, and section 1.2 continues that idea with explorations with patterns. Students will be able to understand and explain. So one of the things we're going to do is finding patterns and determining if a pattern holds. Deductive and inductive reasoning and when to use them, different types of sequences such as arithmetic, geometric, and Fibonacci, finding the nth term of a certain sequence, using differences to find a pattern for neither arithmetic nor geometric sequences. So we're going to start off with an example, and we want to describe any patterns that we see here. So take a look at what we've got going on. Notice we've got 1 plus 0 times 9 equals 11. And in the second line, 2 plus 1 times 9 equals 11. Third line, 3 plus 12 times 9 equals 111. 4 plus 123 times 9 equals 1,111. Of course, you see pattern here, right? So notice it points out there are several possible patterns. For example, the numbers on the far left are natural numbers. Notice they work up from 1, 2, 3, 4, 5. Notice the numbers in the middle are products of two numbers, the second of which is 9. Notice there's a 9 in all 5 of our lines here. And the first number in the first product is 0. After that, the first number is formed by using the natural numbers and including one more in each successive line. So again, we start with 0 in the first line, and then 1, and then 12, which is really a 1 and a 2, and 123, which is really 1, 2, 3, right? And then 1, 2, 3, 4. Now, can you write the next line? That's really, you recognize if you know a pattern, if you can write the next line. And by the way, I didn't address the patterns over here on the right, but the next slide likely does. The resulting numbers on the right are formed using ones and include an additional 1 in each successive line. Pretty neat, huh? Now the real question is, do the patterns continue, and why or why not? So we would need to come up with an example. Now let's follow the pattern. Let's just maybe write an example of what would come next. Now you might have to go back and look at what we had before. Let's do that real quick. There we go. So we left off at 5, and then 1, 2, 3, 4. Notice these are the numbers below 5 times 9 equals 11,111, which is 5 ones over here. So the next one in line, let's just put it on this page because that'll make it a little bit easier, would be 6 plus, and then that would be 1, 2, 3, 4, 5 times 9, and that should equal, and we will check it, 1, 2, 3, 4, 5, 6 ones if the pattern holds. So if you have your calculator nearby, how about you multiply that out and see if it's true? And you better believe I checked it myself, and it is true. So, could you continue on? Where do you think you might run into issues? What if, here's the question I have. What about the 9 one right here? If we put a 9, so that'd be 9 plus, and then we would do 1, 2, 3, 4, 5, 6, 7, 8 times 9. Does that really equal? Now the answer should be, see, 1, 2, 3, 4, 5, 6. It'd be 9 ones. Does this still hold? Again, check it. And lo and behold, it does. It really does hold. But does that mean it would hold for every number? Again, where do I think we might run into issues? Well, what if this number was like 14? Would that even make sense? So if we had a 14 here, then we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 9. And that would equal to 14 ones over here. We could try that out. Or I've got an example already for you. Here we go. So look, there 13. We've got 13 written up right here. So again, notice your pattern. Okay, so I got 13, which means these numbers should go all the way to 12, right? So notice 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 9. But look, this is definitely not 13 ones over here. So what probably threw it off whack is, or out of whack, or off whack, however you want to say it, is when we got bigger than 10 over here. That could cause problems. As a matter of fact, you might not even be able to go past 9. I didn't check it past that. But once you find one example that breaks the pattern, that would be a counter example. That would be a reason the pattern doesn't hold. So keep that in mind. So some patterns only hold for certain values, which would be the case with this really cool example, but it doesn't hold for every single number. By the way, the reasoning the book gives in this bottom paragraph, it says the pattern breaks down when the pattern of digits and the number being multiplied by 9 contains previously used digits. What do they mean by that? Well, right here, so we get to 9, but then we've got a 1, we've got a 0, which is not previously used, but the one's previously used. 1, 1, 1, 2. All those are previously used digits. So it was fine until we got up to 9. But then when you go to 10, we've got previously used digits. Now let's talk about inductive reasoning. You make generalizations based on observations and patterns. It may lead to a conjecture, which is a statement that is thought to be true but hasn't been proved. So it's just an idea. It's a thought of what could happen and may be true. And finally, can be proven false by a counterexample. Y'all, that's what we did just a minute ago, right? When we did 13 or 14, then we have a counterexample why the particular pattern doesn't hold true, okay? Now, the book gives a warning about making conjectures, the danger of making conjectures, let it say that. I mean, you want to make conjectures to see if a pattern holds, but you don't want to assume. You need to prove that your conjecture is true, or you just can't assume it's true. And they've got a really neat example here. Notice it says, choose points on a circle and connect them to form distinct, non-overlapping regions. So if you pick 2 points and connect the dots, that gives you 2 regions. If you pick 3 points on the circle and connect the dots, notice that gives us 4 regions. 1, 2, 3, 4. If you pick 4 points and you connect the dots, here, 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 okay, and then across here, connect. You see, in every way possible. So from this particular point, let me use my highlighter here to make sure you're clear on what we're doing. From one particular point here, we connect this point, and this point. Then we move over to another point, and we connect here, which we've already connected that way, but we need to connect here and here. And then finally, I move over to this point, pick a different color, and we've already connected here and here, but we haven't connected to that point over there. Notice that divides into the highest number is 8 regions when we have 4 points. Now here's the question. Say we want to try to guess a formula for this or make a pattern out of this. So when we had 2 points, we had 2 regions. Okay, we add another point, and now we have 4 regions. You add another point, and now we have 8 regions. Okay, so 2 points, 2 regions. You add a point, and then the 2 regions doubles to 8. And then you add a point, and the 4 regions doubles, the 2, I said that wrong, doubles to 4. Then the 4 regions double to 8. So I bet if we keep following this pattern, if we take this to 5 points, would we guess that we would double it again and we would get 16 regions if this holds? What do you think? Now the book says, it appears that each time we increase the number of points by 1, we double the number of regions. Hey, that's what we were thinking, right? If this were true, then for 5 points, we would have 2 times the number of regions with 4 points, or 16. And that's what we said, right? With 5 points, we would likely have 16 regions. Notice they're using 2 to the 4th. So if we made up our own, so say we wanted to know if we had 7 points, right? Then that would be 2 to the 6th, wouldn't it? If 5 points we had 2 to the 4th, and 7 points we would have 2 to the 6th. Or they go on to say here, if we base our conjecture on the pattern, we might believe that for 10 points, we would have 2 to the 9th, or 512 regions. That's a lot of regions, y'all. Now look at this diagram here. We have a circle, and count the points 1, 2, 3, 4, 5. 5 points on our circle. How many regions do we have? And it looks like, counted out, it is 16, with a 16 landing in the middle. That was what our guess was, right? It's looking pretty good. All right, let's look at another example then. For 6 points, remember that would be 2 to the 5th, we should have 32. Do we have 32? I'm inspecting this picture, and I'm not seeing a 32 right off the bat. If we read the bottom, there are actually 31 regions. So the conjecture is not true. And likely for, what was it, 10 points? It was like 2 to the 9th, which was 512 regions. That's likely not true too. But all you have to do is find one time that the pattern breaks, and you would say that the pattern is not true. Or you'd have to narrow it down and say the pattern is only true up to a certain value, or between some particular range or domain of values. So we wanted to find an arithmetic sequence. So a sequence is an ordered arrangement of numbers, figures, or objects. You just put commas between them. Sequences can be classified by their properties. So if they have certain properties, it'll make it a certain type of sequence. So we want to talk about an arithmetic sequence. We haven't gotten there yet. That's a sequence in which each successive term is obtained from the previous term by addition or subtraction of a fixed number. So it'll be the same number between each of the numbers. So notice you've got this particular sequence here, 2, 5, 8, 11, 14. What's the difference between 2 and 5? It's 3, right? What's the difference between 5 and 8? That's also 3. The difference between 11 and 14, 14 minus 11 is 3. So if you continue that pattern, you definitely have an arithmetic sequence with the difference between each term is 3. That's a classic arithmetic sequence. Okay, so let's check out an interesting sequence. It says, find a pattern in the number of matchsticks required to continue the pattern. Okay, so the pattern in matchsticks. So this, notice it's separated by commas. So how many matchsticks do we have here? We have 4. How many do we have here? Let's count them. We had 4 to start with, and then we added 1, 2, 3. So that's 7. Okay, now look, it took this pattern and added another piece at the end down here. So again, what's new compared to the line before is the purple part there. So it looks like we added 3 to that. Again, it's 10, or you could just count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Well, commas between these guys. And how many down here? Now again, what's new? Well, this same pattern is here, and at the end we have our new piece there. So 10 plus 3 more gives me 13. Now what do you notice? The difference between each of these terms is 3. What would the next one be? Without even a picture, I bet you that would be 16, right? And then 19, and then add 3 more. So this would be a arithmetic sequence, right? And to summarize, it says, note that the addition of a square to an arrangement requires the addition of 3 matchsticks each time. Thus, the numerical pattern obtained is 4, 7, 10, 13, 16, 19, just like we said, an arithmetic sequence with a difference of 3. So yay, the matchsticks is an arithmetic sequence. So find the first 4 terms of a sequence given by and determine whether the sequence seems to be arithmetic. All right? So the number of the terms. So this is saying the first one in line is 7. The second term in line is 11. The third term is 15, and the fourth term is 19. Okay, would you say that's an arithmetic sequence? Well, they're all 4 apart, are they not? So again, 4 here, 4 here, 4 here. If you listed these terms, it would be 7, 11, 15, 19. What would be next? So 19 and 4, 23 and 4, 27 if we keep following the pattern. But it is definitely an arithmetic sequence with a difference of 4. Now look at the way that's written out. Okay, so you have the first sequence. We multiply the difference times 1 and add 3. This is kind of like a starting point or a shift to our problem. Okay, and then the second one we did 4 times 2. Again, the second term we multiply the 4 times 2 and add that base of 3. The third term we multiply 4 by 3 and add that base of 3. And then the fourth term we multiply 4 by 4 and then add that 3. So definitely a arithmetic sequence and a pattern that might help you write sequences. Now here we have a different problem. Find the first 4 terms of a sequence given by a sub n, or the nth term is n squared minus 1, and determine whether the sequence seems to be arithmetic. Can we do that? Sure we can, right? So the nth term, so my a sub 1, if I use the formula, my a sub 1, just which means my first term is equal to, now my n is 1, so I plug that into my formula. 1 squared minus 1. We know 1 squared is 1 minus 1, and 1 minus 1 is 0. So my first term is 0. Then a sub 2, which means my second term, is 2 squared minus 1, which we know is 4 minus 1, which is 3. My third term is 3 squared minus 1, which is 9 minus 1, which is 8. And then let's look at our fourth term. A sub 4 is 4 squared minus 1, which is 16 minus 1, which is 15. Now the question is, they want to know, first of all, the term value, 0, 3, 8, 15, and is this arithmetic? Well, the difference between 0 and 3 is 3. The difference between 3 and 8 is 5. And the difference between 8 and 15 is 7. So is it arithmetic? No, it's not, because the difference between each successive term must be constant. It must be the same number every time. Now here's just a typed up version of exactly what we just did together. So there's our terms that we calculated, 0, 3, 8, and 15, and the comment is to the right. The sequence is not arithmetic because it has no common difference. When you subtract those terms, you don't get the same number each time. So let's try example 4 and see what we can do. The diagrams in the figure show the molecular structure of alkanes. A class of hydrocarbons, C, represents a carbon atom, and H, a hydrogen atom. Didn't know we were going to do chemistry, did you? A connecting segment shows a chemical bond, and they also make the remark that CH4 stands for C1H4. All right, so how do these bond? So notice methane, that's listed right here, has a carbon with 4 hydrogens, okay? And then ethane, I assume that's how you pronounce that. You've got the 2 carbons, and then again off you have hydrogens. And then propane has 3 carbons, and then you see the arrangement of hydrogens. Now here's the real question. It says hectane is an alkane with 100 carbon atoms. How many hydrogen atoms does it have? Can we figure this out, right? Hectane is an alkane with 100 carbon atoms. So you can see the C's lined up 100 across in your mind, right? How many hydrogen atoms does it have? Let's go take a look at our picture that we had up just a minute ago. There we go. Now, you think we can develop a pattern from this and figure this out? So it looks like with one carbon atom, we had 4 hydrogen atoms, right? Okay. With 2 carbon atoms, we had 1, 2, 3, 4, 5, 6. Now notice the ones on the end stay for everyone. So all of these are a given every single time. No matter how many carbons you have those end guys, right? All right. But what about the ones I don't have circled? The up and down ones. So if you have 1 carbon, then you have 1 on the top and the bottom. So that's going to be 2 hydrogens. And then you add the 2 end guys. Look, if you have 2 carbons, then you have 4 hydrogens. And then you add the 2 end guys. If you have 3 carbons, right, then you have 1, 2, 3, 4, 5, 6, 8 hydrogens, and then you add the 2 end guys. So it looks like, doesn't it look like to you we're just doubling the hydrogen because, doubling the carbons because there's just 1 on top and 1 on the bottom. So every time you have a carbon, you double the hydrogens, 1 on top, 1 on bottom. Then you add the 2 on the ends. Does that seem like a good pattern to you? Again, so what would happen if we had 4? Let's just picture it, right? We have 4 carbons. And we'll do it at the top of the page. Y'all hang with me. So 1, 2, 3, 4 carbons. Let's make my hydrogen a different color. Then we have an H on top, H on bottom, H on top, H on bottom, H on top, H on bottom. Yeah, I'll say it again. There we go. So 4 times 2 is 8 of them. But then you have to add those 2 end guys. So it's double the number of carbons plus 2. So we could just write some cute formula, which would be 2 times the carbons plus the 2 on the ends. Does that work for you? I'm feeling it. It works for me. So we back to our big question. If I can get back to our big question. There it is. So hectane is an alkane with 100 carbons. So it's going to be 2 times the carbons, and then we're going to add 2. Well, our carbons is 100, so 2 times 100. Then we're going to add 2, which, you have to multiply before you add. So that's going to be 200 plus 2, which is 202, if I could write it. Now, how does the book say to do it? Let's find out. It says, hectane is an alkane with 100 carbon atoms. Oh, we read that. First, study the drawing of the alkanes and disregard the extreme left and the right hydrogen atoms in each. Hey, we did that, right? With this restriction, we see that for every carbon atom, there are 2 hydrogen atoms, right? We double it. Therefore, there are twice as many hydrogen atoms as carbon atoms, plus the 2 end guys, right? The 2 hydrogen atoms at the extremes. Hey, we did it. We came up with our very own formula from just looking at a pattern. So you can do this. And look at this summary. Does this look familiar to you? So the number of carbon atoms is 1. We said 2 times 1 plus 2. Now, let me remind you, sometimes when we put stuff in equation form or table form, people freak out on me. Remember those 2 right there? Those are the end guys. The book called it the extremes. So these are our end guys. We keep adding the same number every time. And this is our 2C. 2 times the number of carbon atoms. So when we did 100, that was the question they asked, was 2 times 100 plus 2. That's that 202 that we calculated correctly. Yay, go us. And look at this nice fancy formula down here at the bottom. For N atoms, it would just be 2N plus 2. And look, you did some chemistry today. Organic chemistry today. Yay. Now let's try another problem where we get to apply possibly this arithmetic sequence thing that we're learning here. A theater is set up in such a way that there are 20 seats in the first row and 4 additional seats in each consecutive row. So again, the first row might have 20 seats, or does have 20 seats. The second row has 24. What would the third row have? 28, right? And then 32. So 4 additional seats each row until you get to the last row, and they say that has 144 seats. So we would need to know how many rows are there in the theater. Now, one way you could do this is you could just list the numbers between 20 and 144 with their differences 4, like 20, add 4, that's 24, add 4, that's 28, add 4, that's 32, and write them all down until you get to 144 and count how many rows you have. But how about we try to use a formula that we have, right? Now, the first in the series, the first row in the series, or our A sub 1 value, is 20. So that is the lowest. So again, we could write down A sub 1 is 20. Now, what is the difference between all the rows? Well, the difference, which they're going to call D, is 4, right? What else do we know? Well, we also know that A sub n, the last row, right, is 144. What we're looking for, right, is n. We don't know what the n value is. We don't know how many rows. The first row has 20, the last row has 144, and the difference is 4 between them. Now, using an arithmetic sequence formula, we could say that A sub n is equal to A sub 1, where you start, plus, now we have to multiply something times the difference. I'm just going to put D. Our difference is 4. We'll plug that in just a minute, but something times the difference. Now here's the thing though. A sub 1 is just 20. So if we're imagining what needs to go here, excuse me. Okay, you guys, I lost my train of thought because I had a phone call, and I don't even want to edit. We're on a roll. I don't even want to edit this video. So we are looking at our formula over here, right? So A sub n, that just means any term, not just the last one, but any term is equal to A sub 1. That's going to be our 20. It's where the sequence starts. Plus something times the difference. Every time we're going to be adding that 4 to it. Now, if I plug in like an n value right here, like the first sequence, A sub 1, if I plug in 1 right here, that would give me 20 plus 4. So that's not going to work, y'all. I'm going to have to put n minus 1 inside of here, because when I plug in 20 here, and then that is the first term in our sequence, then 1 minus 1 is 0, so I don't add the 4. And then when I do the second term, then it's still 20 plus 2, because it's the second term. 2 minus 1 is 1 times 4. That'd be 20 plus 4 is 24. Hey, this is working now, right? And then I plug in 3. Remember, my third term is 28. We already know this. And so that would be 20. That stays 20 no matter what. Plus 3 minus 1 is 2 times 4 is 8. 20 plus 8 is 28. This is working. So y'all, this is our formula. This is our fancy formula right here that we want to use. Now let's see what the book says about this. Here we go. Okay, look, so A sub 1 is 20. Remember what A sub 1 means? That just means it's your first term in the sequence. A sub n, our last term in the sequence, is 144. D, the difference is 4. So if we write a formula for this, it's A sub n equals A sub 1, our first term in the sequence, right? Plus n minus 1, because if you just plug in n, then we would start with our first term being 24, not 20. And so this needs to be 0 the first time we add. And times our 4. We got this. So let's substitute into this formula, right? Here we go. So A sub n, that's our last row, 144, is equal to 20, right? This is our, so 144 is our last row. 20 is our A sub 1, our first row. N minus 1, That's what we multiply times the 4 to get to the correct row. And remember, 4 is our difference right here. Let's do the algebra. You want to? What would you do next if you're trying to solve for n? A lot of you would probably distribute the 4 inside, add like terms. You could even subtract the 20, divide by 4, add 1. There's different ways that you can handle this. Here's what we did. So distribute the 4. Matter of fact, they subtracted the 20. Look. Don't let this make you nervous. Minus 20, right? 144 minus 20 is 124. Equals n minus 1 times 4. Now, how about we get rid of that 4? How could we do that? Hey, let's divide this side by 4 and this side by 4. Now, all my inking is going to disappear. And it's going to give you that line. 124 divided by 4 is 31 is equal to n minus 1. What algebra step do we do now? Let's add 1 and add 1. That gives you 32 is equal to n. What does that mean? There are 32 rows, right? I did it ahead. But there we go. N is 32, and there are 32 rows in the theater. Remember, we talked about units, how important units are, and I highly suggest writing your answer when it has units in a sentence so it's very clear you have found what is asked for. There are 32 rows in this theater. Hey, I've already reached my 30-minute mark, so I'm going to shut this one down. I'm going to open up a part 2 to section 1.2, and I'll be right back. If I don't talk to you for a while, you have a wonderful day.